In this video, we'll look at relationships between variables. We use contingency tables and clustered bar graphs to describe the relationship between two categorical variables. A contingency table shows frequencies for each level of the variables simultaneously. There's a row variable and a column variable. This table also provides marginal totals, the total count within each level of each variable. If you want to display percentages, be sure that they are calculated based on levels of the explanatory variable, or which came first. Gender is the explanatory variable here, so each column will sum to 100%. We interpret the relationship by comparing cell percentages across columns for each value of the other variable, which indicates here that men and women are about equally represented within degree categories. This table shows the relationship between passenger class and survival on the Titanic. Before getting percentages, we identify the explanatory variable, which is passenger class. From the marginal total, we see that less than 1/3 of all passengers survived. But when we compare percentages across passenger class, a relationship emerges. Nearly 2/3 of first-class passengers survived, and third-class passengers and crew members were least likely to survive. Because there are only two survival categories, we only need to examine one of them. The interpretation is the same. This clustered bar graph shows the relationship between gender and degree earned, clustered by gender. Categories for the other variable are displayed on the x-axis. Here are the Titanic data, clustered by passenger class. So bars for the same passenger class will sum to 100%. When one variable is categorical and the other is quantitative, we create a table or bar graph with means and standard deviations of the quantitative variable for each level of the categorical variable. We can also use histograms or box plots to show the relationship graphically. Here's a table of means and standard deviations for debonding force for different bonding agents. Bonding agent is the categorical independent variable with 6 levels, and force needed to debond is the quantitative dependent variable. This bar graph shows mean bond strength for 5 materials. The whiskers at the top of each bar indicate standard deviations. We can also describe the relationship graphically using histograms or box plots. Here, it's easy to see a difference in both central tendency and dispersion. The relationship between two quantitative variables is shown graphically in a scatter plot, with each subject's scores on the two variables depicted as a dot on a grid. When looking at a scatter plot, we focus on its linearity as well as the direction and strength of the relationship. We also look for possible outliers. Here are a few examples. If there is an explanatory variable, it always goes on the x-axis. The first scatter plot shows a positive direction. As values for x increase, so do values for y. One might see this kind of a relationship between SAT scores and GRE or DAT scores. The second scatter plot shows just the opposite. As values for x increase, values for y decrease. An example might be the relationship between alcohol consumption and fine motor coordination. In this scatter plot, it's hard to see any sort of a pattern. There's no apparent correlation between the two variables, something you would expect for two unrelated characteristics, such as creativity and athletic ability. This scatter plot shows a relationship that's not linear, but curvilinear. Scores for y increase with increasing values of x up to a point, and then decrease. You might see this pattern for something like anxiety and test performance. We need a little bit of anxiety or stress or we wouldn't get out of bed in the morning, but too much and we can't function. The correlation coefficient, R, is a numeric indicator of the nature and strength of a relationship between variables and tells us how well the relationship can be described by a straight line. R can range between -1 and +1, and the sign indicates the direction of the relationship. A -1 indicates a perfect negative correlation, and a +1 indicates a perfect positive correlation. In both cases, all data points fall on a straight line. The absolute value of R indicates the strength of the relationship. This scatter plot shows city and highway mileage for 16 different vehicle types. This looks quite linear. As miles per gallon for city driving increase, so do miles per gallon on the highway, so the direction is positive. It also appears to be a fairly strong relationship, as the points are all clustered close to an imaginary line that we could draw through the data. In looking for outliers, we might be drawn to this data point, but it follows the general pattern of the rest of the data, even though the values for x and y are low. This shows mean scores on 2 sections of the Scholastic Aptitude Test for 8 different groups of students. The relationship appears mostly linear and positive. As verbal scores increase, so do math scores. It's also very strong. You can visualize a line that comes very close to most of these data points. This score seems to be an exception. The math score is higher than expected based on the verbal score, and vice versa. This shows the relationship between emissions of 2 air pollutants. It's a fairly linear negative relationship. As one pollutant increases, the other decreases. It also appears to be a moderate to strong relationship. There seems to be a slight curve, but most of the dots are not too far from a fitted straight line. This score seems to be an exception to the pattern. The amount of nitrogen oxide is higher than any other vehicle, but to fit the straight line, the carbon monoxide value would have to have been negative. A strong correlation does not indicate that one variable causes the other. A correlation is just that, co-relation. For example, an article reported a strong positive relationship between a country's per capita chocolate consumption and the number of Nobel laureates. The author noted that it remains to be determined whether chocolate consumption is the causative mechanism, but he decided that it was likely that chocolate plays a role. The importance of descriptive statistics cannot be overemphasized. One must understand the data, including relationships among variables, and identify any potential issues so that they may be managed. Descriptive statistics are also reported as part of study results. Most research involves collecting data and testing hypotheses, but before getting to that step, we describe the variables and relationships among them, using the numerical and graphical descriptive statistics presented in this series.